1, here's 2, here's the graph of the function, the same thing. But this time, I'm asked to use the midpoint, 0.5. Midpoint, 1.5. So the area M2 is base, still 1, times height, but that is f of 0.5, plus base times height, still 1, times f of 1.5. So let's see what we get. In y equals, I'm going to put this function as x squared and then plus 1. And I'm going to plug in 0.5, and I'm going to plug in 1.5, and then when I add 1.25 to 3.25, I have 4.5. Which of these three scenarios is the best option for this function? Which of these three scenarios has the least amount of error? That's it. Best. Best result. Well, obviously, 4.5 will definitely be between 3 and 7 for this particular function. Okay, here's the next scenario. I don't want n equals 2. Not good. I should say not good enough. Not enough. Not good enough. What about, you think, what would happen with n equals 4? In other words, the area with the leftmost point with 4 subintervals. Yeah, let's just look at one scenario. Which one would you like to look at with 4 subintervals?
The midpoint.
The midpoint. Excellent. Let's do the midpoint. I agree. Since I want 4 subintervals, I divide everything equally. So the number, the width, we're going to call that in a minute delta x. Width of each subinterval. How do I determine delta x? 2 minus 0 divided by 4, which is indeed 0.5. So this time I have 4 subintervals, and I'm using the midpoint, so we want to determine the area with the midpoint with 4 subintervals. This is what we want to find. Okay, the midpoint will be 0.25, and this will be the height, and this will be the area. Here I have 0.75, here is the height, and here's the area of the rectangle. This is 1.25, here's the height, here is the area, and this is 1.75. Here is the height, and here is the rectangle. So then, the area M4 equals, the width of each subinterval is 0.5. This time I want to pull it out. I don't want to write base times height, base times height, base times, no, I want to pull this out already, because each and every one of them will be multiplied by delta x. F of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. And let's get a number. Here's how I like to do this, but there are other options. I like to create a list. So in stat, and is this calculator different than, what is my edit? Yes, I want to edit. So I have something in those lists, so I'm clearing those lists, and I'm clearing.
Sorry, how did you
Yeah.
get there?
Yeah, so let's do that. So let me start from the beginning. So am I recording this? Yes, I am recording. Okay. So second and list. So let me erase everything. Okay. Second and list. And it gives us names. Without the second. Yeah, with the second. Yes, edit. So I want to edit the, so second and list will not work. So just press stat. So not second and list, just stat. And we want to edit. So press edit. In list L1, I want to put these numbers. 0.25, 0.75, 1.25, and 1.75. 0.25, enter, 0.75, enter, 1.25, enter, and 1.75, enter. Now, go to the second list and highlight the top of the list where it says L2. I hope you can follow this. I'll do it again. So where it says L2, and now we're going to enter for L2 0.5 in parentheses the function x squared plus 1. But instead of x, sorry, I have to put the list L1. Second and list L1 squared plus 1. And close the parenthesis. So one more time, what am I trying to do? So I entered what changes, 0.25, 0.75, 1.25, and 1.75 in here. Now I want this list to calculate for each and every one of them the product 0.5 times this, and put it in the first row, second column. 0.5 times f of 0.75, 0.5 times f of 0.75, and put the number in here. So when I press enter, I get all those numbers at once. And now I want to determine the sum of this. And then I go to stats and I want to calculate. And it's a one variable stats, and it is for list L2, and I want to calculate. And it gives me the sum. And now the reason why I wanted to show you this is because I want you to see that the summation notation has a wide application. It's all over, including in statistics. So this is the sum of all x values in list L2, 4.625. So this is 4.625. Is this exact area?
No.
Absolutely not. Excellent. It's not the exact area. Perfect. Here's my next question. And that will lead us to what we want to accomplish today. Okay. So with two subintervals, not good. With 4 subintervals, you still said it's not the exact area. If I go to 8, is that better?
Could be better.
Good. But is it the exact area?
No.
No. So how many subintervals will please you? So what will you say the area will be exact with, don't write anything on the side, I haven't finished. So exact with how many subintervals? What will please you? What will, you will say, oh, okay, with that n, I know it's going to be exact. You said no, absolutely, to 2. You said no to 4. You said no to 8. I'm sure you're going to say no to 16. I'm sure you're going to say no to 128. I'm sure you're going to say no till when? So all these are no. Not good enough for the exact area. But what will please you? And you'll say, oh, yeah, that one I will be happy with. How?
Either infinity or n.
Excellent. Excellent. Infinity. Infinity will please me. I will say that's definitely exact. Good. What does that mean? There is a concept in this course that we talked about a lot, even in the previous chapter, and that we looked at infinity. What is that? What is the concept that we looked at with infinity? It's connected to infinity, and we talked about it in chapter 2 and in chapter 3 and in chapter 4.
Limit?
Thank you very much. You thought you would get away from it? The limit. As the number of subintervals approaches, you already told me what will please you then?
Infinity.
Exactly. Of, this will be the sum of areas of all rectangles. In other words, for all subintervals. If it's a sum, we just discussed the notation a minute ago. What notation would that be? The
Summation notation.
very good. From I being the first subinterval till the last one, what are we summing up? We're summing up areas of rectangles. Base times height, plus base times height, plus base times height, plus base times height. So this is the base, we call it delta x, times, this is delta x. What is this? It's f of x. But we are going to have to connect it to this, because it's not always the same. See here, for the first subinterval is f of 0.25, but for the second subinterval is f of 0.075. So that's not the same always. For this point is f of 1.25. It's a different one. For this point is f of 1.75, a different one. This piece is the Riemann sum, and this is the exact area. So this is the exact area. Guaranteed. Now, we are ready to determine the area that is the exact area for the function we started with. We started with this function. We want to determine, using the limit of the Riemann sum, we want to determine the area, the exact area, no approximation, no 2 intervals, 4, 6, 8, whatever. We want to determine the exact area under the graph of x squared plus 1 on the interval 0, 2, using the limit of the Riemann sum. So that's our problem next. Use the limit of the Riemann sum to find no approximation, to find the exact area under f of x, x squared plus 1, and the x-axis, of course, on 0, 2. Okay. As you know, the first problem will take me forever, and then the next and the next and the next will take much less. We have 3 preps. We can start. I can't put all this together, put it together to find the limit, because I need 3 pieces. I need to determine this. I need to determine this inside, and then I need to determine this. 1, 2, 3. So first, number 1, delta x. Delta x, by definition, for any interval a comma b, is b minus a over n. Specifically, in our case, delta x will be 2 minus 0 over n. I finally found this piece. Prep number 2. xi. Again, what does this xi mean? For the first subinterval is 0.25. For the second subinterval is 0.75. For the next is 1.25. For the next is 1.75. For I equals 1 is this. For I equals 2 is this. And so on and so forth. So it's constantly changing from one interval to the other. So let's look and see what this is equal to. This is the interval 0 to 2. And I divide it into n subintervals. Each subinterval has this width of 2 over n. This piece is 2 over n, or delta x. This piece is delta x. This piece is delta x. This piece is delta x. Everything is delta x. I divided the interval between 0 and 2 into n subintervals of the same width. Maybe I should write it here. Width of each subinterval. Now, before we write this, we are not ready yet. This is x1, right here. This is x2. This is x3. So from 0, the first subinterval gives us x1. So this is x1. This point is x1, which is 0 plus 1 delta x. When I move on to the next subinterval, I get x2, which is 0, plus 2 delta x. When I move on to x3, I have 0 plus 3 delta x. If this is not 0, if it's 5, then I'll write 5, but it's 0. But this is xi. Can anyone tell us, in general, from I equals 1 through n, what will xi equal to for our case?
Is 0 plus I delta x?
That's it. When x is 1, I have 1. When x is 2, I have 2. When x is 3, I have 3. When x is I have I. 0, there is no need to write. Delta x, I will replace it by 2 over n. So this is 2i over n. That's my xi 2I over n. Final prep. So I have this, I have the inside, but now I want this. Just plug it in the function. So remember the function is x squared plus 1. I'm going to plug in 2I over n. F of 2I over n. No problem, plug it in here. 2I over n squared plus 1 is 4I squared over n squared plus 1. Finally, I can say I have